Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world.
So for today's episode, it gives me great pleasure to welcome Robert Rossi to the show. He's the SVP of Autonomous Systems at a fantastic company called TuSimple. Welcome to the show, Robert.
Thank you, Ryan.
Great. And if we could start out by getting to know you a bit better, if you could tell us about your background and where you're from, that would be fantastic.
Okay, so I guess the first thing is everybody somewhat is a context of the childhood and the environment that they came from. I grew up in Detroit in the city. I grew up at a time when the microprocessor, the image processor, the very first personal computers were being innovated. And in Detroit, there was a big focus on applying the new microprocessor technology to automation and robotics. Okay, and this was in the 1976, 1977 timeframe. At that time, I got quite interested and I started molding my education. Went to a different special high school called Cass Tech in Detroit. It's a very well-known high school with a rich history. And after going there in high school, I got hired by General Motors.
In high school?
Yeah, in high school. 16 years old. The day I turned 16, I got hired by General Motors. And they asked me, where did I want to work? And I said, well, when I was a few years earlier, when I was 13, I went on a field trip to the tech center at General Motors in Warren, Michigan. And somebody showed me a computer vision system. Okay, analyzing parts on a conveyor belt. I was so fascinated that the group moved on and I lost them. And I couldn't find the group that I was with. I was just fascinated by computer vision. Okay. And so I think that was kind of the seed for me was I started at my career at General Motors. And the first assignment that I had was figuring out a way to inspect the quality of cars being built, especially the sheet metal assemblies in the car, using lasers and image processing. Okay.
Oh, wow. And that was was that in the 70s or the 80s?
1978, 1979.
So that's like, I mean, we think of those things
pre-PC, right?
Yeah. Sort of analog circuits, and I mean that would have been like super cutting edge at the time.
Right. So I mean, the sensor basically had to communicate analog information back to like a mini computer. Okay.
Yeah.
And do analog to digital conversion and it was very expensive and it was very cutting edge for, and what we were only focusing on the areas of the car that were dangerous if they came apart, like your seat back, the sheet metal assembly for the seat of the car, things like that.
Yeah.
I went to Michigan Tech, continuing on this co-op program with General Motors. And after my second year, I had an idea to create a sensor where all the processing was done in the sensor. Okay. And I prototyped it and ended up starting a company at the age of 20.
Wow.
That was developing laser inspection systems for automotive quality analysis of automotive manufacturing.
Wow.
So that's when I got my start. The year was 1982. I initially got exposed kind of academically to AI technology in 1979, and it was just a stroke of luck. I walked into a rare bookstore, and they had 2 paperback books from MIT kind of that were surveying the whole field, all of the technologies, natural language, computer vision, different kinds of things like this, a 2-book series. And so the minute I made money with the laser sensors, we started looking at the other aspects of moving up the chain of processing, right? Doing statistical analysis and then diagnostic reasoning. And that's when I really jumped into AI right? And started working. So around the 1983, 84 timeframe, I started working on symbolic artificial intelligence combined with statistical analysis of signals.
So at this point, I am literally gobsmacked.
What's that?
I think most people would think, and me particularly, that these things are like really new. You know, it's the current, it's the trend, it's on. But you were in the 80s working on AI and computer vision systems.
Yeah, and adaptive control for welding, the whole visual servoing for robotics. It was all going on, but probably General Motors at the time was a leader in manufacturing. It's one of the biggest manufacturing companies in the world at the time, right? And so, and the tech center was the center of innovation. I just got lucky based on context, I think. Okay.
Yeah.
So, so my journey kind of started there. We had our ups and downs over the years. It was very successful for about 6-7 years. Ross Perot, guy who ran for president, came in and kind of wiped out that automation industry in Detroit when he sold his company to General Motors.
Cool.
And I went to work for a company called Inference Corporation, which was a founding company in symbolic artificial intelligence. I think it was the first commercial venture in AI,
right.
Founded in Los Angeles with a guy from UC Irvine and executive from Hughes Aircraft. So I went to work there, and then the whole thing with that early generation of expert systems type technology kind of was going on in the 80s, okay? And I jumped to another startup in Palo Alto called Neuron Data, okay?
Yeah.
And again, it was an expert system engine, a deployment architecture, and I would work on custom applications for large customers that would combine methods, statistical methods, the reasoning methods available in the engine, different kinds of contributing elements of doing AI. So this was in the late 80s. I continued with that company through the 90s. I moved to Wall Street. I ended up working on trading applications and some defense applications, kind of rotated between Washington, D.C., New York City, Boston, up and down the East Coast, working for all kinds of things related to defense, to telecommunications, to business applications, and especially Wall Street financial applications.
You were saying, talking about your engine just there, like what were these?
Well, the thing was like in Wall Street, we used Sun Microsystems, right? Computers, which were something between a mini computer and it was a Unix workstation, we called them at the time. Okay. We did work with neural nets at the time. Okay. So we were processing time series data on Wall Street, and there were a lot of this was done on a regular PC with a add-in card that would do the matrix computations that you do on a GPU today. So that there were vendors selling expensive cards that were completely dedicated to doing matrix computations, so supporting matrix computations way back then. Yeah. And so, and the general thing is that you had a very simple neural net. It literally had 3 layers and a very wide center layer, but the computation was limited, and many times an experiment would take weeks to run before you got feedback cycles. So that was the real problem, is your iteration cycle wasn't that good. And in the 90s, there was a big reset on the neural net stuff back to support vector machines and some other statistical based approaches to doing things that were a little bit more computationally tractable. So we kind of had that winter, right, for neural nets almost for 15 years, starting in the early 90s and then going to the zeros. In 1998, I decided to leave Neuron Data, which became Blaze Software, and actually ended up going public in year 2000, right before the dot-com crash. So I formed a company that was basically working on Siri and Cortana. And the idea at the time, the bandwidth on the cell phone was very low. I had the idea of a personal assistant, that had all kinds of context about you, so it could resolve natural language queries using the context that it had. Like, it knew about your calendar, it knew about what you were doing, different kinds of things like that. But the problem is that you did not have enough bandwidth to send a compressed audio back to a service environment. Okay. So the innovation was speaker dependent phoneme recognition. Okay. That would be done in the phone, and created a way to simulate vocal tract of the human, the human vocal tract, and parameterize it and develop an adaptive filter with the job of extracting phonemes, the fundamental speech artifacts that are under words, okay, out of the language, then processing that in a cloud infrastructure. That venture put a lot of my own money into it that came from the previous ventures. The dot-com crash happened, kind of weathered through that, but then 9/11 happened. And the door shut on almost everything. There was one vendor in speech called Nuance that was doing pretty good despite all of those conditions. But basically the venture capital door was closed. I started looking for an acquirer or partner, and ended up going to Microsoft. We onboarded the technology, but had some resistance from other technologies there. I was at Microsoft for a couple of years before I got frustrated with that. And then I ended up being put in charge of the media processing core team at Microsoft. Okay. So that was all of the image, video, all of the compression technologies, DSP technologies that are on the Windows platform, Xbox, mobile devices, and kind of reference architectures for the extended ecosystem of people making consumer electronics devices. Anyhow, that was an unbelievable experience. Microsoft was a really defining thing, because I learned an enormous amount about managing large, complicated technology products. Windows at the time was 50 million lines of code. We were a core team, so if you didn't do your job right, the pipeline team, the media player team, the internet browser, right, all of these products would have problems. So even though it wasn't like the risk that you have with an autonomous system, rolling out a update to 1 billion people was painful. And so you learn how to do really complicated things and deal with a massively complicated architecture, and learn how to incrementally evolve it, okay, and then do releases in a predictable way. And so that was an unbelievable experience for me. When I was there, we started, there's a tie-in kind of to what we do today and why I'm at TuSimple. When I was there, we had developed a competitive technology to H.264 called VC1, okay? And it was a high definition video coding technology. And we were after the royalties from optical media at the time, which would have been Blu-ray and HD DVD, which was killed. And to do that, to win that game, we wanted to build the best encoders for Hollywood movies. Yeah. And to do that, we began studying how do you proportion the distortion in the image, right? Where can you save bits, and where do you need bits? Okay. And to do that, you had to understand human attention and how it would interact with the media. Normally, this was derivable because the videographer or the cameraman had intent in the way he was framing the scene, right? So we learned, we created technology, and this was our first use of GPUs. This was before CUDA, where we were using shader languages for texture shaders, right? Which had all the linear algebra stuff on it. To perform technologies to analyze where the attention should be in these images, and where to focus, where the human viewing the content would be focusing their eyes. Wow. Okay? And then bury the distortion in areas they weren't paying attention to. Oh. That is an amazing tie-in to why I came to TuSimple, actually. That'll tie in. In 2009, I left, and I wanted to combine the knowledge that I learned at Microsoft with my previous passion for robotics. And the idea then was to create something called cloud robotics, where you could have a device like a lawnmower, like a riding lawnmower. And you say, okay, riding lawnmower is only in use once a week, but a lot of people would prefer to have that time and go do something else on Saturday. Okay, right? but you're not going to put $5,000 or $10,000 worth of electronics in your lawnmower that's in use once a week, unless you're incredibly wealthy.
Yeah.
Okay. Right. So, and what if you could use the same framework to support many different functionalities, like the compute architecture could support your security cameras at night, but during the day could analyze the imagery and control your oven. Okay. Or control your robot mowing the lawn or so you could use the same brain to interface to different robotic devices that had sensors and actuators on it and very little memory. Okay. Very, very cost embedded electronics. So we started working on that, ended up creating some really amazing autonomous robot demonstrations, including aerial drones designed for agriculture. Ran into a lot of problems. I didn't realize the U.S. government was not really happy about that formula of technology. And so ran into a lot of resistance. I ended up with a few years then fumbling. It's one of the things that entrepreneurs, you kind of have to time when the world is ready for the technology that you're in, right?
Yeah.
You can make a big mistake being too early, actually.
Yep. It's the sort of Goldilocks effect of too early, too late, just right is
right. If I had to wind back, and I wish I would have somebody mentor me in timing, right? Of when you time a venture. The first one I hit right. The first time I raised money for a venture, I walked into venture capitalists and they said, my stuff is 1/10 the cost of the existing solutions that you've already funded. It's going to kill your businesses. Right?
Yeah.
So anyways, fumbled around in the 2010 to 2015. I worked in augmented reality, did a couple other things. I worked for Boeing on the robots for manufacture of the carbon fiber aircraft. And then around 2015, I went to work for this really interesting startup called Civil Maps. And Civil Maps was one of the first companies. They originally started doing maps for the rail system, okay, and vegetation and different kinds of things like that. But then the autonomous vehicle thing was catching on, and they went into developing high-def maps for autonomous driving. And they were specifically focused on visual localization. How do you localize without a reliance on GPS, a GNSS system? Yeah. Okay. And doing that with LiDAR and a way of encoding a signature or a fingerprint of the environment. Okay. So I worked with them for a short while. Then I moved on to an augmented reality venture, see-through augmented reality. I also had some stuff I did in optics. So I designed an interesting passive augmented reality, see-through augmented reality system that used the phone as the entire engine, rendering everything. Okay. You can see it on my LinkedIn page. See, it's my proudest innovation, actually, because optically it was a really crazy thing optically. So after that, gosh, I can't remember all my positions I had. A couple robotics companies I spent short stints at. Then I was hired by TomTom in the Netherlands, in Amsterdam. Okay. And to lead as senior vice president their autonomous systems, HD maps for autonomous vehicles, for autonomous driving. So I worked there, but right when I got there, COVID broke out. My fiance wasn't able to come, and we spent 18 months apart. And finally, I got tired of that. Yeah, and I started come back to the United States. So.
Right. So you actually relocated from the US to the Netherlands?
Yeah, I did.
Oh, wow. Big move. Really big move.
Yeah, that was probably the greatest period of uncertainty imaginable, because right when I got there, COVID broke out, and then you had no support from anybody, and you didn't speak the language. All the communications was in Dutch. Yeah, it was a crazy time. But I'll never remember. I will never forget it, because I lived in probably the most interesting area of Amsterdam, one of the nicest streets. It was called the Paris of Amsterdam. And I got to spend a lot of time reading and studying things that I didn't get the time to do in the normal life that I had. It was just, so it was almost a year and a half of a really deep immersion and futuristic things. So it was there that somebody contacted me on LinkedIn, and at first I didn't respond to the recruiter's kind of inquiry. It was very vague about some company in the autonomous vehicle space. And I didn't pay attention to it. And about 2 weeks later, I saw something with an announcement between NVIDIA and this company called TuSimple.
Yeah.
And that's when I took another peek at it. And then I went into it and I took a look at, the founder and what his background was. And, I liked the idea of the trucking space. I thought it was an easier to accomplish problem. And so I called the guy back and I said, if the company you sent the message about is TuSimple, I'm interested in talking to you about that one. And so things went really fast after a matter of days. I went through several interviews and over the weekend, everything, right? And then the following week, I joined TuSimple. I guess that could lead us into a little bit of the background of TuSimple.
Yeah, it'd be great to sort of know more about the company and what they do and sort of how that came into being for people that haven't come across them before.
So I think if you really wind back with TuSimple, you have to start with our founder, Xiaodi Hao. And you have to wind back to probably 2008, okay, when he was studying what to do with his thesis. And from my conversations with him, he was inspired by a guy that was one of the 4 founders of artificial intelligence, Herbert Simon. And Herbert Simon was both somebody who studied operations research and economics, okay, and then artificial intelligence. He was kind of unique in this combination. We were very knowledgeable of him. The oldest book I have on AI is called Human Problem Solving, which was written in 1972. And so he's a very famous guy. And he basically had a communications on something called the attention economy. And he basically said, the fundamental task of intelligence is filtering the massive amount of information that you're presented with. So the human brain only uses 12 watts. Only 10% of it max is active at any one point in time. Okay. Right. And we are faced, especially driving a car at 65, 75 miles an hour, you are consuming a massive amount of information.
Yeah.
Okay. Potentially for all the sensors that you have. So the fundamental goal becomes, how do you sort out what you pay attention to and what you disregard? And right now that has infected every aspect of deep learning. That is the core of the technologies that you have in ChatGPT, all the transformer architectures, things like that. It's all centered around this concept that the most important thing is attention. In fact, the revolutionary article that was done a year after Xiaodi did his thesis was attention's all you need, right? That's the famous paper that led to all the stuff going on in natural language and the things that we have today. So Xiaodi decided to do in 2008 his thesis in this area. He was at Caltech under Christopher Koch. That's also the university that produced people like Carver Mead that were very dedicated to investigating biologically plausible models of information processing in the retina. That was Carver Mead.
Yeah.
Koch in the nervous system architecture, different kinds of things like that. And so Xiaodi kind of really got himself aligned with the very deepest researchers in this area. And then he focused, along with the guy at UCLA, I think Alan Ewell, he had a lot of interactions there as well. But the focus of his PhD thesis, which took 6 years to complete, was based on this concept of attention and biologically plausible mechanisms, okay, derived from analyzing the human nervous system, okay, of how attention is performed in different areas of the brain. After he did his thesis, he's like, okay, now what do I do? I got to go make money, right? And my thesis is not immediately in the area of an interest, right?
Yeah.
But his timing was pretty good for autonomous vehicles. And the general principle of you have the advantage of being able to position and mount sensors of all types, all spectrums, all distances, right, all around the vehicle, but you have an overload potentially of information that you have to filter through.
Yeah.
How you do that contextually, right, as the road situation is changing, as the environment changes, as your task goal changes, right? How do you direct and control your attention? So I think the unique thing about TuSimple is that is the core elements of our DNA of our company. Okay, this foundation that Xiaodi laid in that attention was a key element of solving this problem. And combined with deep learning, what are the ways that we can leverage deep learning models and architectures, right, that leverage this attention principle to an advantage, to have a superior processing across all of the available places we could sense, and then how we interpret that and integrate that and drive it in a goal-directed fashion. So if you study a lot about neuroscience and neuropsychology, right, one of the things that you'll come across is that we think we're reacting to information, but we're not. We're parsing, we are literally parsing what we see in a goal and task-oriented fashion with some interrupts that come from peripheral vision and things like that. But generally, we have a task and we are parsing in a strategic way what we encounter with our sensory system to solve that task.
Yeah, I see what you mean. It's interesting. Winding back to what you said earlier, about the human brain, that was a really interesting comment. 12 watts of power, but it's a remarkably energy efficient given what it achieves. Because you've got in an autonomous driving system probably, I don't know, a kilowatt of computing power?
5,000 watts.
5 kilowatts of computing power, and you're not quite able to do what we can do with 12 watts.
No, so we have things to learn, right? We have things to learn in terms of dimensionality reduction, post-processing of high-dimensional data. There's quite a few things that fundamentally, part of this will be solved once the architecture stabilizes and we can make dedicated processors, right? To saying post-process your LiDAR data, post-process your radar data, post-process your camera data, okay? Before it's presented to the rest of the pipeline. But to get back on that track, so that was the kind of the foundation of TuSimple. Took a couple years for the company to kind of get traction, build its first vehicles, and begin the kind of road to, I think things really started to come together in 2018 when it had some demonstrable technology that was interesting enough to attract some tier 1 and OEM players to pay attention. Okay. Things moved pretty fast from there, and kind of led to the IPO the company had in a perfectly timed IPO market in the year 2000. Okay. And I joined right at the IPO. I was in the S1 document. I had made the decision maybe a month before the IPO happened. Right.
Right. So good timing again.
Yeah. That was better timing than previous. I wasn't exactly too late. It wasn't too early. So maybe that's how I got here. And I came to TuSimple to lead the HD Maps division of the company. Since then, I've also run operations, test operations, and now I head the whole technology realm for autonomous systems.
When you're looking at it, the sort of concept of focusing attention. So in your autonomous stack, how do you go about doing that? 'Cause, I mean, you've got a lot of different sensor inputs. You've got a lot of stuff going on there. But what do you actually mean when you're saying like your sort of core principle is focusing the attention? What is that?
Okay, so you have two kind of things. They're somewhat semantically related, but they're different. Okay, one is how does the deep learning architecture have attention mechanisms that focuses how it trains and adapts? Okay, right. That's a core principle that's behind the whole era of transformers, encoders, and decoders that are the current architecture that you have for processing sequences. Okay. So a lot of times when you a few years ago, when you would do these type of architectures, you would have sensor data, and then you would have a convolutional neural network, right? That was the paradigm at the time, right? You would do object recognition, perhaps some scene decomposition, different kinds of tests like this, right? And then you would have subsequent reasoning that you do to try and fuse these things using a variety of technologies. Sometimes that was fuzzy logic, sometimes it was rule-based systems. There was a variety of different methods that you could use, both statistical and non-statistical, to do that. In the deep learning in the deep learning era, or technology, around the 2000 plus timeframe, they began starting to process sequences. Okay, because most things that we encounter are sequences. Okay, right? Our most reasoning that we do is establish initial track on something, then we process a sequence of things. That's like anchoring your attention and then following what happens after that. Most of the efforts that were going on in natural language, you clearly have to process a sequence. You have to process the relative relationships of words in a sentence, the relationships of one sentence to a previous sentence, okay? A group of sentences to a previous chapter to the original context and information of what the book's related to, things like this. So we're sequence processors, right? And deep learning architectures evolved first for recurrent neural networks, and then they had these things called gated recurrent units and long short-term memory. All of these were feedback circuits. So they started having the deep learning architectures feed back into themselves. Okay. Right. And with this, they had a memory mechanism, and the memory mechanism, kind of like dynamic programming, right, is storing a history, right, of a summary of the history. And it allows you to process a new input with existing context that you have about that input. Okay. The thing that TuSimple did was, all of this technology was evolving in natural language, but we got on the leading edge very early of reconfiguring how you formulate the input, okay, into this type of architecture for computer vision. And that was a big thing where we shifted from the paradigm of people processing individual images to processing sequences, okay, and streams of information, stream processing. So that was very key, and I think we were very, very early and uniquely differentiated in that regard as a company.
TuSimple as a business is very much focused on the sort of practical. You are building, you build vehicles, you're operating vehicles, you're gathering that data. What's the kind of, obviously that in itself, you're gaining a lot of data and experience from doing that. What do you see as being the end goal for that?
If you kind of pop yourself up and say, what is our purpose? Why do we exist? What is our reason for living as a company? Okay. Our purpose is to harness the power of artificial intelligence and basically disrupt and innovate and make a better method of freight transportation. Okay, right? Basically, that's more reliable, lower cost, okay, more resilient, okay, more easily available, and works 7/24. Okay, that's the business thesis. And by the massive lowering of cost of getting the driver and all of the related support for the drivers out of the equation, okay, there is the potential to go beyond what human capability is in performing this task. Okay. And in many ways we do that right now. Okay.
Yeah.
So that's kind of the purpose of the company. Okay. Now, if you have a vision, let's project ourselves out 10 years to 2033, right? Envision 10,000 trucks on the road, hundreds of terminals, all driver out autonomous freight, operating in a coordinated and efficient manner. OEMs building trucks, okay, that are based on this technology where it's built for the safety requirements uses high volume manufacturing techniques, all of that kind of stuff, right? So then if you pop back and you say, okay, that I got it. That's our purpose. That's our vision, right? What's our mission? Okay. And our mission is to catalyze the ecosystem of everybody that's required to do this. Okay. And that's a tough thing. Okay. Right. Because you have to say, okay, I'm a tiny company, by compared to the industry players, right?
Yeah.
You've got to catalyze the tier one ecosystem, making everything from redundant steering and braking systems to sensors and NVIDIA GPUs and all of this stuff, right? You're trying to build a system and at least show the capability, okay, right, of these parts being brought together for a new concept. And that we've done an amazing job.
Yeah.
Okay. So you're trying to catalyze this ecosystem around this massive opportunity where this would be almost impossible for most of them to do. Okay. But at the end of the day, we want other carriers to run freight using our technology, right? We want other people to build the trucks. Okay. Right.
Yeah.
We want to focus on the tough task of maintaining, evolving, and growing the capability of the trucks to operate in a larger operational domain, okay, and perform in a safe, increasingly safer manner.
Yeah.
Learn from all of the experiences of all the deployed trucks to evolve the technology, things like that.
So your sort of longer term future, whilst you're sort of building and running truck trials and stuff right today, in the future, your sort of business model will be supplying your technology into established truck manufacturers, basically. So,
right. So primarily, we will be a cloud service-based software company. Okay, right. That'll be the large essence of it. Okay, and we will, the ultimate income model will be a revenue per mile equation. Okay, that you're renting a brain. Right, to pilot the vehicle.
Do you see the market being all sort of, vehicle OEM and new vehicle stuff, or are you kind of also dealing with the ultimate end user as well? So the sort of the big kind of end fleets and.
So the thing, if you think about a truck company like J.B. Hunt, okay, they were formed in 1962, right? It took for them to evolve the network that they have took, 60 years. Okay. 60 plus years. Okay. It would take us the same amount of time if we try to do that from scratch. So the way to scale is to build the technology in a way that without massively disrupting them, right? Massively disrupting the way they do business today, to have this technology be consumed by them in a successful way. Okay. And that means certain challenges, like how do you, when you get to a carrier terminal, how do you navigate inside that terminal when there's other people driven trucks? Okay. In that environment, and it's not necessarily structured or mappable. You end up with these interesting challenges, right? That you have to address one step at a time. So the reason why we do a TuSimple network first, right, is we can structure that a little bit better. We can make a structured terminal, okay, with a landing and launching pad and the various services that we need for this upfit model of trucks that we have. And then we can do drayage, which is that final link to the destination, right? And which consumes some of your profits, okay, on the run, right? We have a mandatory network we have to do to actually get to the way we can hand stuff off to the carrier. We have to perfect the way the whole system works. It's not just about the autonomous vehicle. It's everything that happens at both ends of the trip, okay, and everything that supports the trip on the back end during operation.
I would imagine that in the last couple of years, that the market has kind of tipped on its head in terms of these big operators now having particularly acute problems with labor shortages.
Like UPS. Right?
Yeah, so they just can't get the staff. So it's gone from kind of people thinking, yeah, this is going to be a nice thing in the future. We can see cost savings. We can see it'd be like a nice to have that our business could evolve into that. Whereas I imagine at the moment, it's kind of becoming oh my goodness, if only we could have this like now, it would solve a lot of headaches. Is the market really, has it changed in that kind of way?
So if you think about it, you started off before COVID, you were pushing on a rope, right? You're basically saying, we're going to innovate this stuff. It's going to save you money. Okay. You'll make more profits. You could price your product lower. Yeah. Okay. Right. That's a promise, but it's a long ways off.
It was like, yeah, that's cool. But we'll have it when it's,
talk to us in 10 years, but we'll be real when you finish it. Okay. Right. Then COVID happened. Okay. And there's deep analyses about fundamental flows that we're relying on that are not resilient to something like that. Okay. For instance, just-in-time inventory, there's no buffering, okay, of product, okay? Yeah. Buffering is done by the cargo that's in the trailer, okay, in motion, okay, right? Yeah. The fragility of extreme over-optimization in just-in-time inventory flows, right, like for parts in the auto industry, things like that, right? We're really exposed by this, okay? Secondly, in COVID, then you had a driver shortage problem, okay? And it's significant and it's growing. It's continuing to grow, okay? You also have an aging population. So if you look at the average age of a truck driver, it's very similar to agriculture, right? Where it's in the 60s, okay? Right? The average age is in the 60s. You're in trouble, okay? Unless you have another technology solution, right? Or a way to incentivize people to get into that field, right?
It's a difficult life. I mean, trucks are difficult.
Hard on your body.
Yeah. My father was a truck driver, right? And unfortunately, he passed away when he was 67. Heart condition, heart attack. But he was, he struggled with his weight, and that kind of life behind the wheel is very difficult to maintain your health. And, I think a lot of people in that industry are in a similar situation. It's not an easy job, and it's not a job a lot of young people even want to do. So it's a really difficult.
It's like at the beginning in the late 70s, we're working on spot welding inside the factory, robots for spot welding, right? And yeah, you took away some jobs, but were those good jobs? The average person using spot welder had back injuries because the apparatus was very heavy. Yeah. You had to orient it in a funky way, right? Then when you hit the thing, if you didn't have it all lined up right, you got burned with sparks all over your body, right? Not all jobs are really that good.
Yeah, well, it's the same. I sort of have this thing with, the area that I live in, when I grew up, it was sort of all coal mining, right? And the coal mining jobs went, but, people get all sentimental about it. But did you, wasn't a great job, shortened your life expectancy quite significantly. So it's an important, from a societal perspective, there's all these complex drivers of the aging population, the shrinking workforce, the special skills, etc. And the pressure that is creating on a lot of sectors, because it's not just truck drivers that there's a shortage of. There's a shortage of just about everything. But you've got the ability to solve that problem with the kind of technology that TuSimple are developing. I don't know if I want to say. I don't even know if I want to say it like this, but I'm going to. So, being realistic, and I kind of hate. I will leave that there. Being realistic, how far away do you think it is as a sort of solution that could be adopted at a scale that's kind of equivalent to the problem?
Let's pick a target though. Let's say 10 years from now, 10,000 trucks on the U.S. interstate system from TuSimple. Let's just envision that. Okay. Right? Try to test whether it's realistic to achieve in the time frame of 10 years. Right? So to do that, you kind of have to work your way backwards. You say, what you need is an OEM that took a massive risk. Okay. Right? He committed a ton of money and a ton of NRE and accepted a massive disruptive change in very similar to electric vehicles, right? But way more complex, right? And figured out all elements of this, from maintenance, maintenance stuff, the ecosystem of parts providers, field replaceable unit design of the stuff in the truck, right? ASIL D, or safety certified electronics, right? So you have to kind of work your way backwards, right? And what is it that they fundamentally need, right? Well, the fundamental thing, and I think some of the other AV companies don't get this, and it's kind of distorted by the robotaxi market in autonomous, right? Is that there's kind of one plan that says, you saturate a very limited ODD, right? Like you go down in Texas and you focus in the Texas Triangle, and you say there's a certain volume of trucks flowing on those links, 10 to 30,000 trucks per day on those links, right? We're just going to saturate that environment and build a custom solution for a Texas Triangle. No OEM is going to do that. No OEM is going to build a truck for the Texas Triangle, okay? If you succeed in an upfit model, you still are not succeeding in your long-range plan, okay? Your long-range plan is to get that OEM comfortable enough where they feel confident about the whole system of things that they need to do to commit and make that happen at scale. When you do that, you get the high volume manufacturing, which is normally 10,000 units and above, okay? That you need for fixtured, printed circuit board and roboticized printed circuit board assembly and automated testing and all the various things that you need to do things. So when we look at it from a strategic perspective, you work your way back from 10 years and you say, what do they need 3 years before that, right? What do they need in the 7th year, right? What do they need now? What do they need in 3 years from now? It's all about getting them to that point where they can commit and coordinate and influence and take the bet with the tier one ecosystem, and also get the timing of the players in the supply chain, okay, aligned and agreed that timing point is the right timing point. Because if you cannot do that, you've got 90% of your equations, but you're still a mechanical liar, which is not really a solution, okay, right? You need solid state liar, right? So that's really the goal that you need to do. And the way we see that is we go from what we're doing right now to we have to go to a substantial sized upfit fleet, okay, that operates on a substantial operational ODD, right? Lower half of the United States. That's enough for the OEM, okay, right? East to West Coast, lower half of the United States, pretty good, okay? We'll evolve to more challenging weather conditions and terrains and things like that later, okay? Probably with the exact same truck, just software upgrades, okay? So basically, we need to get to the point from now, maybe in the next 2 years, right, where you kind of are stabilizing on what the ecosystem of hardware needs to be, okay, right? What the partitioning of the system needs to be, okay, so that you can figure out how the ecosystem kind of coordinates and delivers the solution in pieces, okay, and how they fit together, right? 2 years from now, we have to have that together, okay? Then once they commit, okay, there's a period of time where we have to build trucks on early parts, kind of this evolving scenario, right? And build out a fleet to test out a substantial operational design domain, okay? And so in that phase, I think we have to build a fleet of 100 to 1,000 trucks, okay? In using the current upfit model, but potentially aligning with a redundant base platform of the truck that has redundant steering and redundant braking.
It's quite a significant challenge, I guess. I mean, from all of that, because a number of the OEMs talk about this kind of technology and it being in their roadmap and things that they're actively working on. And you've obviously got the legacy OEMs, and then there's one particular company that I'm going to ask you about. Do you see the sort of much OEM-driven activity that is equivalent to what you're doing?
I think what's happening right now is the truck industry. You realize in the truck market, some companies just make a base truck platform, and then some other company goes and builds an ambulance, right, or a fire truck or something like that, right. And in doing that, the manufacturer builds a base platform. They build a chassis, it's got brakes on it, it's got engines, it's got some other stuff, and somebody else builds a cab and all the other stuff. Okay. The OEM industry is now at the point where they're ready to build that base chassis. Okay. Right. That's specific to support L4. And meanwhile, they're off doing other things that are kind of baby steps towards this goal in L2 plus type technologies.
The OEM that's kind of potentially taking a different approach, and I guess sort of you could say famously takes a different approach in terms of its autonomous system, but has jumped into the trucking market, and I think a lot of that is because of this is Tesla. And what do you think of what they're doing?
So the thing, I'm not going to go. I haven't done detail analysis of Tesla's as a customer, but I will say it's something they have as a business and a technology model that's spot on, and it couldn't have been articulated better than by Ford Motor Company CEO recently in a blog post, right? So right now, Ford, if it wants to update software, right, it's got 100 vendors to talk. Okay, right? You got a bunch of ECUs, you got a bunch of stuff, and it's like making a change to the software on a vehicle that lasts 10 years. Okay, right? It is an absolute nightmare. You got to bring them into the service center, right? You have to have something that you rolled out that does it, right? It's a non-winning strategy. And Tesla evolved, they managed the entire software for the whole thing themselves, okay? And actually the processing technology. We have to do that too. So we have to work with the OEM so that we are that continuous integration, continuous deployment pipeline, right? For the entire software complex, right? That's on the vehicle. And so I think that people who don't get that model will not realize that this is going to be an evolving technology. Okay. Right. If you're an OEM, think about it, right? You're an OEM and you build 10,000 trucks, they're on the road, they're doing their thing. And then all of a sudden you're having crashes that happen, right? In a particular scenario. And you realize there's a deficit. You got to roll out a change. You got to be able to roll out a change, and like ideally you can roll out that change as fast as you can get it done, right? Which kind of lead into our discussion on simulation.
Yeah, it is. I mean, one of the things I really, possibly the thing that excites me about autonomous technology the most, really is not where it starts. It's where it gets to quite quickly. In that sort of complex scenarios like driving, you know, if when I'm driving or you're driving or, you know, something happens, I learn or you learn, you know, but we don't both learn unless we have a discussion about it, you know, over a beer. Oh, this happened. And
sometimes the government learns that this particular type of road intersection causes problems over a common range of people.
But when you've got a significant fleet of vehicles gathering data continuously and learning, even if you have a problem, that experience is stored, like you're saying, in the memory and shared, and the ability to very quickly learn and adapt. You know, and it's exponential, isn't it? The more vehicles you put into the fleet.
That's correct. It gets safer.
Yeah, phenomenally, and the speed at which that can start to happen. You know, it's really exciting. Actually, we start to see that and see what happens with that. You know, as things develop.
So right after we did our driver out test in early 2001, late 2020 to 2021, I kind of led a project for this technology we have called CyberMap. And we realized that part of safety is statistical. Let's say you have a truck and it's going down a 2-lane road and on the highway, and it encounters a wide emergency lane vehicle, right? Okay, which is difficult because now you have to bias in the lane or change into the next lane. You might not have the opportunity to do that, right?
Yeah,
that might lead to the necessity to brake pretty heavily, okay, to speed, right? Especially if there's So if you have the first vehicle that encounters that, you had high risk pass. Potentially was able to window chase and cut into the next lane. Potentially was able to bias sufficiently.
Yeah,
maybe it had to slow down, right? But what if you instantly communicated that to the rest of the trucks on the fleet? Okay, right? And they're knowledgeable of that emergency lane vehicle two kilometers before it comes into their perceptual horizon, and they move over into the other lane. They pass the scenario with zero risk.
Yeah.
Okay. And that could be 20 subsequent trucks. Okay. So there's this kind of information dynamic sharing kind of.
Yeah. And we see that a little bit, I mean, there's sort of, again, like famously for our human brains with Waze, like that's the.
Yeah. It's the same concept as Waze, right? It's just, and it's kind of interesting. It's like the perception system in one truck is communicating something it saw to the cloud, and then the other trucks are pulling the cloud, and then they get this information that's used in the planning logic, their planning logic. Okay, right? And maybe their perception system says, okay, I'm going to see something off in the distance. I already have a prior that says you're expecting an emergency lane vehicle. It's on the right side of the road because off at 1,000 kilometers beyond, you cannot tell which side of the road it's. Right?
Yeah. Some damage or some debris on the road, or even a damaged section of road that then if you hit it too fast, it's going to cause damage to the truck. And the whole thing is.
And we can have human in the loop for that type of processing as well. Okay, right. So in the CyberMap system, you could have much more comprehensive deep learning technology discriminate the kind of things that are on the road. What are they? What are these weird objects that we see that we can't train the system in because we don't train the system to see refrigerators in the lane. Right.
But it happens.
Right. We had a plane land in front of us on one of our trips, right, on the highways, right?
Not an everyday experience either. Yeah.
So you kind of have that kind of information sharing and learning, which is a social kind of social learning of the environment. Okay, and updating environment, right?
What we should do actually is go back to, because my poor attention distracted us.
Let's circle back to that. We talked about the problems with shortage of drivers, aging driver population, the fact that the job is not that great on the human body.
Yeah,
right?
Yeah.
So you have probably a less reliable workforce as a result, different kinds of things like that. And maybe it's just not a great thing for them long-term for longevity. Right?
Yeah.
But you also have you have an opportunity and a problem. Okay. The problem is human attention, right? And the younger people that go into this field are heavily distracted. They're increasingly taught to flitter between many different attention areas dynamically instead of sustained attention. Okay. And the long range, if you look at the U.S. interstate system, it was designed. We had the opportunity, unlike other countries, right? Brand new country. Okay, let's figure out a way to build a gigantic interstate that connects everything. It's largely long linear segments. For efficiency, right. Unless the train had something that got in your way, right? You just connected up these major things with straight links and then bent them around, mountains and things like that. That is hard on the human attention system to drive in a straight line for 100, 150 miles, 200 miles, let alone 800, 700 miles in one day. So what do? Your attention varies. But when you have an AI system, it doesn't know better than to focus the attention in the way you programmed it.
Yeah.
To focus its attention, right? So it can maintain really rigorous attention, okay, at all times, okay, in all situations without flitting around and getting bored with the current lack of entropy or lack of interesting features, right, that are in the current scene, right, and starting to look at a movie on the phone or something.
It's a huge problem. I mean, that road safety element
Distracted driving and road safety.
So I'm not sure on the statistics for the US, but I think in the UK and Europe, most fatal road accidents involve a truck or a truck hitting passenger cars, and the vast majority of those accidents are caused by distracted drivers. So actually solving that, I mean, it's not just fixing a problem with a labor shortage. You're literally talking about saving lives, and preventing, horrific injuries and loss of life. Normally, if people who are, it's generally not the guy in the truck that unfortunately loses their life. It's the person in the car that gets squashed by the truck.
This is the whole risk equation of trucks versus robotaxis. Robotaxis are typically operating 35 miles an hour and under, okay, and have less than 6,000 pounds of mass or 5,000 pounds of mass, right? We're talking about 75 miles an hour and sometimes 80,000 pounds of mass, okay, right?
Yeah, it can do a lot of damage. So your system, you mentioned earlier that some of your sort of USP is around how you manage the way that the system actually sort of filters and pays attention and I guess dedicates its processing resources to different kind of input streams. How are you doing? What is it about your system that's special in that area? How are you doing that?
Yeah, it's largely in the deep learning architecture. Okay, right. So we use a very, very leading edge way of architecting the system. And I can't go into this too much in detail, but it borrows concepts that are used in modern natural language processing systems that you have behind ChatGPT and BERT and things like that. Okay. And it leverages this concept of transformers. Okay. And they have a concept of encoding things into kind of so think about in natural language, right? You could have a sentence. Okay. Sentence says, Paul went to the store, right? In the conventional way of doing neural net processing, right? It's just a bag of words and you match off of it and you say, what does it mean? Okay. Right. And you would have to match off all combinations of bags of words and do something interesting. The way transformers work is they say, okay, there's something interesting about the sequence and the relationships of the words to one another, right? So they could say, okay, if I anchor the sentence with the word Paul, okay, what is likely to follow Paul from the other words that we have? Paul to, Paul store, or Paul went, okay, right? Paul went statistically is much higher closeness, right? If you study a vast amount of content, right?
Yeah.
You're right. So it says that's a focus area. And then you say, now, if you have Paul went, what's the most likely word after that? Paul went store or Paul went to? Okay. Oh, to is probably a lot better than the or store. The transformer kind of works in this concept of positional encoding. Okay. And you can do the same thing when you index content that is in visual media. All right, like patches of image.
This sounded very similar to some of the things you did in the past with.
Yeah.
Okay.
Yeah. So it's those are the basic concepts, but the idea that you want to do so your fundamental objective is dimensionality reduction. You've got let's say you have a 4K camera, you have millions of pixels, okay, right? And but there's only a couple areas in the image that you're interested in, okay, that are meaningful to you, right? And so what you want to do is you want to blur the rest of the image, right? And you want to focus further processing on the non-blurred stuff because blurred stuff will not be processed, okay? Right. A lot of it is a task like that of saying, how do you blur? And in fact, in old conventional computer vision with erosion and dilation operators, you're doing the same kind of thing manually. You're learning how to discover what things you blur and what things you maintain information about. Okay, right? and concentrate on those areas, right? In subsequent stages of processing, right? And then as you go through this, you say, I kind of did this from the raw pixel to the feature representation. Now I'm going to do it from feature representation to some additional intermediate layer. And then finally, you end up with something we call latent space, or a intermediate representation. Okay, and in technologies like ChatGPT, right, they can study something like natural language, and they can study a sentence. Then they have this way of understanding relationships and closeness of different types of things in language. They can then create a way to say, I understand an intermediate representation that is the meaning of the sentence. Okay. And you come up with this intermediate representation, then you have different decoders. So you have an encoder that creates this intermediate representation. And then the decoders could be anything. You could say, paint a picture. Paul went to the store to paint a picture. Okay. Or you could say, make me a decoder that translates that into French. Right. So you have these different types of decoders, right? And that leads to something we call multitask learning, right? And so this is kind of a direction in the field, I think, that we're leaning.
And this is where you get to you're sort of you have a vision, or your system has vision. It recognizes that is probably a car, that is probably a truck. I need to be more aware of that. That is a tree. I need to be aware of it, but not so aware. And
right. There's other stuff that I don't need to pay attention to. And then as your context changes, you shift your attention, right, based on what's optimal for that scenario, right? So you have a way of dynamically adjusting what that focus is and how you allocate your attention. Okay.
I could probably talk to you all day, and I know that's not going to happen, unfortunately, today, but maybe we'll get the chance of this. It's been absolutely fascinating, really, really fascinating. So just to kind of round off, if you looking forward the next year, maybe a year or two, what are the things that you've got coming up that have got you most excited about the next year or two?
Okay, so I think one of the things is further leveraging our simulation technology. Okay, which is something that we originally were going to talk about. Building up this next generation intermediate fleet that's between now and when we get to commercially built OEM trucks, right? That's in the next few years. We kind of reduced the size of the company, and in doing so, we had certain advantages of being able to see more clearly adjacent parts of the architecture, the actual people. Okay, this is leading to some architectural innovations that make the architecture smaller and more efficient, more unified, right? That we're very excited about. Okay. We use that word unified quite a bit. Yeah. And then there's some big challenges that you have that we are going to face, and everybody else has to face this challenge as well, which involve domain adaptation. Okay. So deep learning systems, when they perform well, they also tend to overfit to a particular environment. Okay. And the concepts of transfer learning and federated learning and also combined with multitask learning, we need to evolve the capability where you don't have a bunch of configurations for different environments, but you have one configuration that is generalized across the wide range of the operational design domain. That is the big challenge that we're looking at.
Thank you so much for taking the time out to talk to me today, Robert. It's been, like I said, absolutely fascinating. I wish you all the best. To people listening, we'll put some links in the show notes so you can find Robert, find TuSimple as a company, some of the other things that we were talking about in the episode. So check out the show notes before. But thank you so much for talking to me today.
Thank you as well. Take care.